You know that shiny chrome on a faucet or the silver on a piece of jewelry, maybe the protective coating on a car part? Well, they all share a secret. It's a hidden science that transforms pretty ordinary materials into objects of beauty and, well, serious durability. So today, let's pull back the curtain on the fascinating process of electroplating. So, how does it happen? How does a dull, raw piece of metal get covered with a completely flawless, brilliant layer of another? The answer isn't magic, not even close. It's a precise and pretty powerful electrochemical process. We're going to break down exactly how that works, right down to the atomic level. You know, the simplest way to think about electroplating is it's kind of like painting with electricity. Seriously. But instead of paint, we're using dissolved metal. And instead of a brush, we're using a really carefully controlled electric current. Basically, what we're doing is running an electric current through a special liquid bath. This current causes dissolved metal ions, tiny metal particles, to form a solid, uniform coating on an object. It's a controlled transformation, and it's all happening at the molecular level. Think of it like this. The object we want to coat, it becomes a magnet for metal. The electric current gives these little positively charged metal particles, we call them ions, the push they need to travel through the solution and literally bond to the object's surface, building up a new layer, one atom at a time. But here's the thing, that coating doesn't just appear all at once. It actually forms in 3 distinct stages. First, these tiny little islands of metal atoms, called nuclei, start popping up all over the surface. Then, these islands start to expand outwards, kind of like ripples in a pond. Finally, they all merge together in a process called film consolidation to create that totally seamless, solid metallic film. Okay, but getting a perfect, durable coating isn't as simple as just flicking a switch. Achieving that flawless finish, it's a lot like baking a cake. It requires the absolute perfect recipe with every single ingredient measured out precisely. So these are the big ones, the crucial control knobs for any electroplating process: the amount of electricity, the chemical makeup of that liquid bath, its temperature, its acidity, and even special additives. Each one dramatically affects the final outcome. Seriously, you mess up just one of these and the whole recipe can be a disaster. All right, let's dive into that first ingredient, current density. And this one is a classic balancing act. If you use too little electrical current, the process is painfully slow and you might end up with a thin, patchy coating. But if you crank it up too high, whoa, you get chaos. The coating can become rough and porous, and you can trigger all these unwanted side reactions, like creating hydrogen bubbles that just ruin the finish. And you know, research really backs this up. There is a sweet spot. As Guler and his colleagues put it, moderate current densities allow controlled uniform deposition. This controlled approach lets the metal atoms lay down nice and evenly, which results in a coating that is not only smooth, but also super hard and strongly bonded to the surface. It just goes to show, in electroplating, control is absolutely everything. And of course, the other ingredients are just as critical. Temperature. That affects how fast the coating builds up and the size of its crystal grains. The pH, or the acidity of the bath, it has to be just right to keep the metal dissolved and stop other chemical reactions from messing things up. And additives? Think of those like secret spices that can make the coating smoother, stronger, and way less stressed. Okay, so you can have the perfect recipe, the most beautiful coating, but it's totally useless if it just peels right off, right? This brings us to probably the single most important factor for a durable product: adhesion. How do you make that new metal layer stick like it was born there? So how do you get it to stick? Well, it really comes down to 2 main secrets. The first is chemical bonding, where the atoms of the new coating form these powerful connections with the object's surface atoms. The second is called mechanical interlocking, where the coating physically grips onto a microscopically rough surface, kind of like how a rock climber needs those little handholds on a cliff face to get a solid grip. Now, to get that bond, you have to do some pretty careful prep work, and this is where it gets really interesting. To get the best finish, you first have to intentionally rough up the surface by etching it. This creates a microtexture for a powerful mechanical grip. Then an activation step creates reactive spots to promote those strong atomic bonds. It's a meticulous process, but it's what creates the foundation for a permanent coating. All right, so we've gone through the science, the recipe, the prep work, but what's the big deal? Why does all this complex stuff matter in our actual everyday lives? Let's connect this lab science to the world around us. The answer is literally everywhere. That brilliant chrome bumper on your car isn't just for looks, it's a shield against rust and impacts. The gold plating on your watch or inside your electronics isn't just beautiful, it provides excellent conductivity and prevents corrosion. At the end of the day, electroplating adds a ton of value by making things last longer, work better, and look incredible. And it all comes back to this one idea. The level of control you have directly impacts the quality. If you have poor control over the recipe, you get defects, coatings that peel right off. Moderate control might give you a passable product, sure, but precise control, getting that current density, temperature, and chemistry just right, that's what yields a superior product with high hardness and unbeatable adhesion. So, what's the big takeaway here? First, electroplating isn't just dipping something in metal. It's a highly controlled science. Second, that recipe of current, temperature, and chemistry is absolutely key. Third, a perfect, lasting finish depends on powerful adhesion from both chemical and mechanical bonds. And finally, this science is a hidden workhorse, improving the things we use every single day. So, the next time you admire a perfectly polished, gleaming metal surface, I hope you won't just see a shiny object. Maybe you'll see the dance of ions, the meticulous surface prep, and that perfectly balanced recipe of electricity and chemistry that made it all possible. Instead of just seeing a finish, what science will you see?